Beyond stepping up our skills at solving systems by having more equations and more variables, we can also step up in a different fashion by having equations that are not linear. They're not lines. So we could have different sorts of equations that would give us quadratics, parabolas. We could have polynomials. We could have, well, absolute values, exponentials, logarithms. We could throw in square roots, cube roots. Basically, though, what we're going to really be leaning more towards is using graphing and substitution. In some cases, elimination is still useful. However, it is a little bit less useful than what we might find with graphing and substitution. Seeing as how what we've got showing up might be a good deal looking like this example here, y equals something else. Those naturally lead themselves to us being able to graph them, whether we do that by hand or with a calculator. Those would naturally lead us to being able to do substitution with y. Well, y equals this, y equals that. Set those two equations equal to one another and solve using our algebra skills. But one of the things that we want to watch out for is that we can now have multiple solutions, not just one solution, but we could have 2 or 3 or 4 or more without actually running up against infinitely many solutions. So we could have a finite number of solutions, 1 or more, and then we still do have those other 2 extreme possibilities. We could still have no solution. We could still have infinitely many solutions. Much more rare that we would have infinitely many solutions in this particular case. And again, they're going to really emphasize a little bit more towards having unique solutions. So just to, again, hit the different kinds of possibilities with some examples, let's start out with the graphing and looking at these 2 equations, y equals x squared minus 3 and y equals 4x minus 6. If we use a little bit of color here, blue on that first equation, what we've got from that particular equation is a parabola. That's going to have a vertex 0, negative 3. And so with my scale, that's going to go right there. And then if I start plugging in points, or if I reference a graph that I've generated on my calculator, I would also have points 1, negative 2, negative 1, negative 2, 2, 1, negative 2, 1, 3, 6, negative 3, 6, and I don't have anything else on this particular grid that I can use to draw in that parabola. So try to sketch that in as best as I can. Not too shabby. The other equation that we've got going on is, and let's use red, still a line, so not trying to jam you up too awful much to get the original ideas across here. We've got a y-intercept of 0, negative 6. Our slope is 4, so that would mean that we would go, for instance, right 1, up 4. Ooh. Right 1, up 4. Oop. Right 1, up 4. Hey, look at that. So we would have what looks to be a line that passes through our parabola, and that's a bit of a tight fit there, but passes through our parabola. It seemed to be at 2 different points. The first one being what looks like positive 1, negative 2. And the second being up here where we have 3, 6. So if we go through the process of checking those in our equations, and we'll talk it through real quick, but I'll leave it to you to actually write stuff down if you'd like. 1 squared minus 3 equals negative 2. 4 times 1 is 4, minus 3 equals negative 2. That checks out. 3, 6. 3 squared is 9, minus 3 is 6. 4 times 3 is 12, minus 6 is 6. So they both, in fact, check out. Same sort of deal with graphing that we had mentioned before. we actually have to have some nice points that we can identify by eye, or even trying to be a little fancier using graphs on the calculator, we would still need to be able to identify those. When stuff gets weird and squirrely, as we know it can get, then graphing would no longer be a serviceable option, and we would have to instead look at stuff like these other two examples, which we're going to work out using our algebra steps. So in that top case, y equals negative 1/3 parentheses x minus 4 parentheses squared plus 4. Second equation, y equals parentheses x minus 2 parentheses squared. In this particular case, we could most naturally use substitution and say we will take the first equation and we will set that equal to the second equation. So we just kind of naturally have a really nice option here. It doesn't always have to work out quite so nicely, but substitution is still going to be a little bit more likely to be of use to us than elimination. So, going through the process of solving here, that means that one of the things that we are not big fans of is that fraction out in front. So we could multiply through by 3, and that would give us a negative out in front, a parentheses x minus 4 squared. 4 times 3 is 12. Over on the right hand side, multiplying by 3 means that a 3 would be now sitting out in front of that set of parentheses. Now I'm in a position where at least there are no more fractions, and I've got stuff trapped inside those parentheses, so I'm going to go ahead and have to do those squares. So being careful about what is out in front of each set of parentheses, let me just do a little bit of that squaring without worrying about anything else. So x minus 4 parentheses squared, I'm going to write that answer inside a set of parentheses here to make sure that I do not accidentally mess something up along the way from having that negative out in front. Over on the right hand side, similar idea, I'm going to do the x minus 2 parentheses squared, but I'm not going to worry about that 3 out front. I'm just going to leave it sitting there for a moment while I do that x squared minus 4x plus 4. Now I'll go ahead and do my distributing here. Negative x squared plus 8x minus 16 plus a 12 equals 3x squared minus 12x plus 12. I'll go ahead and get everything over on the right hand side. So that means that I would have a 4x squared minus 20x and a plus 16, which I can actually transform by dividing through everything by 4. I can get myself an x squared minus 5x plus 4 equals 0. I can go ahead and factor that as x minus 4, x minus 1, setting each of those factors equal to 0 and solving for x means that we would get x equals 4 and x equals 1. Using one or the other of my original equations, and it would be a little bit nicer for us, for instance, to use the second one, we can figure out that, and let's actually split it up this way. Using the second equation, when x is equal to 4, y would be equal to parentheses 4 minus 2 parentheses squared, which would be a 4. When x is equal to 1, y would be equal to parentheses 1 minus 2 parentheses squared, which would be a 1. So we're looking at solutions that seem to be 4, 4, and 1, 1. I'll leave it to you to be able to check those against the original top equation and the original second equation to make sure that both points work in both equations. you should find that that is the case. And while it's a different type of equation to solve, a very similar sort of way of setting things up originally, we have another situation where with y equals and y equals, we can go ahead and begin solving an equation that would basically be take each one and set them equal to each other. This is where we would have to now use some of our equation solving skills for exponents. I would like to be able to write both of these with the same base, so I can transform a 4 into a 2 squared, and that means that I could transform a 1 over 4 into a 1/2 squared, which means that I would then have to also multiply the power of 2 by, actually, we'll just go ahead and put brackets in there for a little extra something something. Multiply those powers together here in just a moment, but again, the first goal here being get the same base on each side. Now I can go ahead and say, yes, my power on the left is equal to my power on the right. And that would end up giving me 4x is equal to 3x minus 5, so therefore x is equal to -5. And if x is equal to -5, I can go in and I can figure out from either the first or the second equation y. So let's just use the first one for argument's sake. 1/4 raised to the power of 2 times -5, which would mean, I'm going to come over to my calculator, parentheses 1/4 power of -10. That'll be fun. 1,048,576. 1,048,576. And so, my solution, and I would still want to check this with both of my original equations, seems to be working out that we would get -5 comma 1,048,576 as our solution. Again, I will leave the check to you to verify that that particular point works in both of our original equations, and therefore that particular point is in fact the correct solution. So, there we go.